Good day, viewers all over the world. I welcome you to today's class. I want to appreciate every one of you that have been watching my videos and I've been sharing them across the globe in all social media platforms. Thank you very much. For those of you who have subscribed and those of you who are yet to subscribe, I still thank every one of you for watching my videos. Please subscribe to my YouTube channel if you have not subscribed. Subscribe and share my videos in your social media platforms across the globe. Once again, my name is Dr. Chris Esekaibe. I am the owner of the YouTube channel Dr. Chris Esekaibe. The essence of the YouTube channel is to teach core topics in applied mathematics and applied statistics, numerical analysis preferably, and applied statistics, to teach key topics and share knowledge across the globe. Please be part of those sharing knowledge across the globe by sharing this video in all your social media platforms. I am a chief lecturer in one of the most prestigious polytechnics here in Nigeria. I hold a doctorate degree in mathematics with distinction, a master's degree in mathematics, and a bachelor's degree in statistics. I specialize in numerical analysis, data analysis and modeling, and scientific computing. I'm a member of the Nigerian Mathematical Society and have published papers in renowned journals, and I've also presented papers in renowned conferences within and outside Nigeria. I work in Nigeria and I live in Nigeria. I am a specialist in mathematics. Please, if you are an AI firm, you do a lot of artificial intelligence. For instance, you try to teach AI models on how to understand mathematical algorithms better. Why not? You can consult me to be part of your team of mathematicians and statisticians. I worked with one US firm. I did a remote job with a US firm, how to teach large language models. You teach them mathematical algorithms. You break the model, stomp the model, and teach the model to understand advanced mathematical algorithms. If you're an AI firm, you do a lot of AI work, especially the mathematical part of it. You can consult me to be part of your team of experts. And also, if you're a research team across the globe, I will be looking forward to hearing from you. Or you're a research student, like somebody in Uganda consulted me, and the person is doing a research in applied mathematics, and I'm contributing my own quota to ensure the person is successful in his MSc thesis. And once again, my contacts are +234 80 330 21903. This first contact is for call and WhatsApp. The second contact is +234 70 6629 7535. This second contact is only for call. Then my email address is written here on the board. I will be looking forward to hearing from you so that I can be part of what you are doing. Please like my videos, share my videos in your social media platforms, and subscribe if you have not subscribed. God bless you as you do that. Please permit me to go into the business of the day. We have a special topic we want to look at today. This topic is key in numerical analysis. As I told you during the introduction, I am a specialist in numerical analysis. Today we shall be looking at second order two-stage explicit Runge-Kutta method for solving initial value problems in ordinary differential equations, ODE, ordinary differential equations. Now, when we talk about the Runge-Kutta methods, Runge-Kutta methods are single-step method or one-step method. They are not multi-step method. They are single-step or one-step method that are used for solving initial value problems in ordinary differential equations. We can also use the Runge-Kutta method to solve stochastic differential equations, not only ordinary differential equations. The differential equation can be first order differential equation. We can also use it to model or solve second order differential equation. But today we shall be looking at this initial value problem. We have boundary value problem, we have initial value problem. This is the general format of an initial value problem. Y prime, you can see, is a first order initial value problem, a first order ordinary differential equations. Ordinary differential equation. The model of the problem is y prime, which is the first derivative, so it's a first order, is equal to f of xn yn. So it's a function of x and y. Then of course x takes value within the interval a and b. Then the initial condition, this is the initial condition, that's why it's called initial value problem. Y of x naught is equal to y naught. Then h is the step length. H is the step length or the mesh size. H is step length or mesh size. So, like for instance, if you have x1 will be given as x naught plus h, then our x2 will be given as x1 plus h, then our x3 will be given as x2 plus h, then our xn plus 1 will be given as xn plus h. So you can see that x, the value for x increases with h. X increases with the mesh size or the step length. That is how it is. So h is always given, then the initial conditions or the initial values are x naught and y naught. So now the second order two-stage explicit Runge-Kutta formula is given as this. Note, the Runge-Kutta formula or methods are iterative. They follow iterative steps. Now, yn plus 1 is given as yn plus 1 over 2 into k1 plus k2. Now, it is two-stage, that's why we are having k1 and k2. So we are considering the two-stage. You can have the second order for three-stage. You can have second order for fourth stage. You can have second order for sixth stage. So it depends on the stage. It depends on how you want to derive it. So, but for this particular class, we shall be looking at second order two-stage. You can see the two stages K1 and K2. So the main equation is y. This is iterative. You can see for you to get yn plus 1, you need yn. So of course you have half into K1 plus K2, where our K1 is given with this formula and the K2 is given by this formula. So today, for this particular class, we shall be considering this initial value problem. This is the initial value problem we want to solve using this second order two-stage explicit Runge-Kutta formula or method. This is an initial value problem, and this is the full format of the initial value problem. If you look at this problem, it's taking this particular format. So here that we have this, it's simply, if you look at this, if our y of 0 is equal to 1, is likely to be our y of x naught to be equal to y naught. This is the initial condition. Look at it here. This is also the initial condition for this initial value problem. So by implication, this simply means that our, look at it, the one in the bracket is 0, the one in the bracket here is x naught. This simply means that our x naught is 0, then of course our y naught is on the right hand side, our y naught is on the right hand side, then our y naught is equal to 1. So these are the initial conditions for this particular problem as given by the problem. And again, we have been given our h to be 0.1. Our h is given to be 0.1. So this is how the second order, second stage Runge-Kutta method works. This is how it works. Now, for every initial value problem, there is the theoretical solution. Now look at this function here. this first derivative, which is the first order differential equation. Now from here, if our y prime is equal to y, then the main function that was this is simply dy over dx, which is the first derivative. Now if I ask a question for us to get the function that was differentiated to get this particular answer, which function are you going to differentiate and you get the same function? Of course, it's an exponential function. So our y of xn will simply be exponential xn. So if it's only an exponential function that will be differentiated and you still arrive at that particular function. Now you can see now if, of course, you can see it from here. If y is equal to exponential x, definitely y prime, which is dy over dx, which is equal to dy all over dx, will simply be exponential x, and this will be simply y. So that is the only function. The exponential function is the only function that you can differentiate or integrate, and it will remain itself. Now you need to also understand the Taylor series expansion of the exponential function. The Taylor series expansion of the exponential function is simply 1 plus x squared over 2 factorial plus x raised to the power 3 all over 3 factorial plus x raised to the power 4 all over 4 factorial plus it is an infinite series. This is the Taylor series expansion of the exponential function. If you come here now, you now want to carry out that differentiation. If I say, for instance, I differentiate few of these terms. If I say d exponential x all over dx, now I'm differentiating it with respect to x. I want to differentiate this Taylor series expansion of exponential x. You will see if I differentiate 1 with respect to x, 1 of course is a constant, it will be 0, plus if I differentiate x with respect to x, I will have 1, then plus if I differentiate x squared, it will be 2x over 2, 2 factorial is 2, 2 will cancel 2, it will be plus x, then plus if I differentiate 3, if I differentiate x cubed, it will be 3x squared. Definitely 3 will cancel 3, it will now be left with 2 factorial. You will now have x squared over 2 factorial. If I also differentiate this, x raised to the power 4, it will be 4x raised to the power 3. 4 will cancel 4. Look at it. Let me differentiate this one. I'm going to have 4x raised to the power 4 all over 4 factorial. That's what I'm going to have here. Of course, this will now give me 4x raised to the power 4 all over 4.3 factorial. You know, 4 factorial is written as 4.3 factorial. 4 will cancel 4. Sorry, 4x raised to the power 3. So you will now see that we are now having x raised to the power 3 over 3 factorial. We come here plus x to the power 3 over 3 factorial plus it continues. So by Taylor series expansion, this is the Taylor series expansion for exponential x, and when you differentiate this particular function with respect to x, you see it repeating itself. That's why if y is equal to exponential x, y prime, which is dy over dx, is equal to exponential x, and that is equal to y. So for this particular initial value problem, the theoretical solution is y of xn is equal to exponential n. So we call this the theoretical solution. That's what we call it. So permit me now to start using the second order two-stage explicit Runge-Kutta formula to solve this particular initial value problem. Permit me to clean this part. You have seen the nature, the format of the initial value problem. H is the make side. Permit me to clean it so that we can start solving immediately. So it is good you have this background understanding. It's good you have the background understanding. Now we want to kickstart. Now the Runge-Kutta methods are iterative methods. So we are going to create a table of solution, a table of results. We can call it table of results. So of course we'll definitely have our number of iterations. We have our xn. Then of course we have our let me take it a bit closer. N, which is the number of iterations. We have our xn. We have our yn. These are the yn means the numerical result. Then we have of our y of xn. These are the theoretical result, and we have our truncation error. So these are the things we are going to get in our table of results. It's very important you understand all this, how they work. It's good you understand how it works. So now it is good we have this particular table, because in numerical analysis, table of results are very important because it enables you to see the error clearly. Now you will understand that from our introduction to numerical analysis, we talked about two major types of errors in numerical analysis. The inherent error. The inherent error is the error that is gotten as a result of rounding off. Now when you use the major solution to the inherent error is taking more decimal places. You can only reduce it. Then the second type of error in numerical analysis is the truncation error. The truncation error is the error you get when you use an approximate formula. Now we want to use an approximate formula to solve this particular problem. That alternate approximate formula is the second order two-stage explicit Runge-Kutta method. Now at the zero iteration, the initial conditions are given. Now when n is 0, here you are talking about x naught, and we have been given to be 0. Then here, from the initial condition we are given to start, these are numerical results. Numerical, and these ones are theoretical. So you should understand the difference between the yn and the y of xn. The y of xn are the theoretical results or the theoretical solution, while yn are the numerical results. So yn here now, our y1 is given as 1.0, which is the initial condition or the initial value given. Now if you take a look at now, our theoretical solution is exponential xn. That is the theoretical solution. Now if you want to get our y of x naught, there's no need writing the values. Our y of x naught, when you say now our x naught is 0, exponential 0 is 1. So here you are going to have y of x naught, and that is equal to what? 1.0. So our error will be, the truncation error is the theoretical solution minus the numerical solution. So the truncation error, this is the formula for the truncation error, is equal to the theoretical solution, just call it T sol minus numerical solution. So for this first one, 1.0 minus 1.0, that is 0.00. So our error at this first iteration is 0.00. Now look at it, for you to get any value for y of xn, you must use exponential xn, because that is theoretical solution. Now at xn, our x naught is 0, so exponential 0 is equal to 1. That is how we got that particular value there. So permit me to just put the values only. Permit me to put the values only. I will be taking it step by step. I will be putting the values only. I will be putting the values only. So for here, when you talk about xn, n is 0, x naught, our x naught is 0. Then when you talk about yn, y naught, our y naught is 1.000. Then when you talk about exponential x and x naught, exponential 0 is 1, is still 1.000. Then now when you now take the difference, the truncation error is the difference between the theoretical solution and the numerical solution. So 1 minus 1 is 0. So at the first stage of iteration is error free, 0.00. Then now let's go straight to the first iteration. We want to go straight to the first iteration. Permit me to clean this part of the board. So we are going straight to the first iteration. Iteration 1. So at iteration 1, our n will be equal to 0. For us to get this particular value, our n will be equal to 0. So now we are starting when n is equal to 0. Look at what we are going to have. 0 plus 1 is 1. We are going to get our y1 will now be equal to y naught, n is 0, plus 1 all over 2 into k1 plus k2. Now we need to get values for k1 and k2. So our k1 will be equal to, look at it here, what is the value of our h? Our h is given to be 0.1. Our h is 0.1. Then f into, now our xn is x naught. Since our n is 0, then comma y naught. So this will now be equal to 0.1 f into, now if you look at it, what is our x naught at the initial condition? Our x naught is 0, comma, what is our y naught? Our y naught is 1. So now you are going to have, remember, when we were writing the initial value problem, we have our y prime is equal to f of xn, comma yn. There's the format. Then compare this with our problem. Our problem here is y prime is equal to y. So this simply means that for f of x and yn, it is y that is f of x and yn. So for this particular problem, our f of x and yn is simply the value of y. That is what it means there. So for this particular problem here now is we are going to have 0.1 into, in place of f of this first value is for x and the second value is for y. But our f of x and yn is only taking the value for y. And what is the value for y? The value for y is 1. So it's 1 that will be put here. So 0.1 times 1, our k1 will be 0.1. That will be the value for our k1. So if we also come again to get our k2, just follow gently. Our k2 will be equal to 0.1. Look at it here now. Then f into, this will now be x naught plus h. What is h? H is 0.1. Then comma, when n is 0, this will be y naught. The y naught, because n is 0, so it will be y naught plus what is our K1? Our K1 is 0.1. You cover the bracket. So this will now come, of course, our H will, of course, 0.1 F into, now, what is our X naught? Our X naught is 0 plus 0.1, it will be 0.1, then you put your comma. What is our Y naught? Our Y naught is 1, then 1 plus 0.1, it will be 1.1. So when you come now, you have your 0.1 times, anytime you see F of course, one value will be for X, the first value will be for X, the second value will be for Y. And we are told that it is Y, so it's the Y value we are going to pick. So you are going to have 0.1 times 1.1, and that will give us the value for our K2. 0.1 times 1.1 will be 0.11. This will now be 0.11. That's what you are going to have. So if you now come here, we can now come and get the value for Y1, since we already have values for K1 and K2. So our Y1 will now be equal to, what is our Y naught? Our Y naught is 1 plus, of course, 1 over 2, you can call it 0.5 into, what is our K1? Our K1 is 0.1 plus K2, our K2 is 0.11. Then you close the bracket, then that will now, when you add these two and multiply it by 0.5, you are going to have 1 plus 0.105. If you add 0.1 to 0.11, you multiply it by 0.5, which is half, you are going to have 0.105. So our Y1 will now be equal to 1.105. So that will be our Y1. So now, when you come here, look at this particular one. Now, we have, for this first iteration now, we are talking about X1. And how do we get our X1? I told us our X1 is simply X0 plus H. And of course, what is our X0? Our X0 is 0 plus H. H is 0.1, so 0.1. So our X1 will be 0.1. You can see X is increasing with H, the mesh size. Now we have been able to get the first, the value for Y1, which is 1.105. That is what we have been able to get. Now, to get the theoretical solution, permit me to clean this part. To get the theoretical solution is also very simple. To get the theoretical solution, now you know that the theoretical solution is y of xn is equal to exponential xn. So this simply means that our y of x1, because that's what we use to get the theoretical solution, will be equal to exponential x1, and that will be equal to exponential, what is our x1? 0.1. Now for us to get exponential 0.1, we are working with 6 decimal places. We are going to have, just press your exponential in your calculator, we are going to have 1.105, 170. So now, if you want to get the error, of course the truncation error, you get the truncation error. The truncation error will be equal to, look at the theoretical solution, 1.105,170 minus 1 which is the minus the numerical solution, 1.105, and that will give us 0.00017. 0.00017. That will now be the error, the truncation error at iteration 1 when n is equal to 1. So you can see how we are making progress. So now again, we are taking one more iteration and we see how we make progress. So now we have seen how we have gotten the iteration 1. Permit me to clean this part and clean these values for k. I will now go again for n is equal to 1. Now, permit me to also clean this part. Now, when n is equal to 1, when n is equal to 1, 1 plus 1 will be 2. So you have your y2 is equal to, of course, you are using your y1 plus 1 all over 2 into k1 plus k2. Now let's get our k1. Our k1 will be equal to, what is our h? H is 0.1, then f into, now this is our xn, x1. You can see it now. So this will now be x1, and our x1 from here is 0.1, so it will be 0.1. Then our y1, of course, yn will be y1, because we are now at the first iteration. What is our y1? Our y1 is 1.1. Y1, the theoretical solution we solve, because we use y1 to get y2, you use y2 to get y3. So our y1 is 1.105. Then if you take this further, it will be 0.1 times. Remember, whenever you see your f of x and y, it is y. So it is the y value you will now pick out. You now take this 0.1 out here, multiplying 1.105. Then when you carry out that multiplication, our k1 will now be equal to 0.1 times 1.105 will be 0.1105. 0.1105. That will be the value for our k1. Now our k1 will now be 0.1105. Now let us get value for our k2. So our k2 will now be equal to, of course, there's our h is 0.1. Then you have your f into, what is our xn? Now at this point n is 1. So our x1 is 0.1. So it's 0.1 plus, of course, h is 0.1. Then comma, what is our yn? Our yn is y1, because at this point n is 1. So our y1 is 1.105 plus our k1. Our k1 is 0.1105. Then you close the bracket. So this will now be equal to 0.1, which is this. Then your f is there. Then you add 0.1 plus 0.1. This will be 0.2. Then of course you now add 1.105 plus, you add 1.105 plus 0.1105, that will be 1.2155. That will be 1.2155. So when you now come, remember, anytime you see f of, remember our f of x and yn will be equal to y, as given by this problem, which is y prime equals to that. So now our k2 will be equal to, of course, our 0.1 times. Remember, this first value is for x, the second value is for y, and this value is for y. That's the one we are going to use. We are going to use 1.2155. So when you multiply 0.1 by 1.2155, we are going to have 0.12155. That will now be the value for our K2. our K2 will now be 0.12155. Now again, since we have gotten values for K1 and K2, it is important we come here to get our Y2, because without K1 and K2 we cannot get our Y2. Our Y2 is now Y1. What's the value for Y1? Our Y1 is 1.105 plus, of course, half is let's take it to decimal, which is 0.5. Now into K1, look at our K1. Our K1 is 0.1105 plus our K2 is 0.12155. Then you close the bracket. Then when you carry out this, you add this to this. Then you get, you multiply it by 0.5. You are going to get 1.221025. 1.22. You are going to get 1.221025. 1.22. Okay, you will see how this is gotten. 1.221025. 1.221025. So this will now be the value for our Y2. 1.221025. Now you can now come and write on the table of results. Now at this particular point, you have when n is equal to 2, of course our x2, of course definitely x2 will be equal to x1 plus h is equal to, what is our x1? 0.1 plus 0.1 is equal to 0.2. So x is increasing with h, so this will be 0.2. The next one 0.3. It keeps going like that. Again, for our y2, the value we go for our y2 is 1.221025. So we are taking up to 6 decimal places. If I'm not mistaken, 6 decimal places, 1, 2, 3, 4, 5, 6. So let us maintain 6 decimal places. Now we have gotten the numerical solution for the second iteration. Now let us get the theoretical solution for that. Now if you want to get the theoretical solution, remember the value for our y of xn is equal to exponential xn. So our y of x2 now will be equal to exponential x2. So that will be exponential 0.2. Now all you just need to do is to press your calculator for exponential 0.2. We are taking it at 2 decimal places. You are going to get 1.221403. 1403. That's what we are going to get. So you can see it now. Just press exponential 0.2. That's what you will get for the theoretical solution. Now our truncation error will be equal to, look at the theoretical solution at iteration 2. It will be 1.221403 minus the numerical solution, which is 1.221025, and that will give you 0.000 0.00378. Let me write it. 0.00038. So 0.00038. That is what the truncation error is. So you can see that at iteration 0, when the initial conditions were given, there was no error. Now at 3 decimal places, they were equal at the first iteration. At the second iteration, also at 3 decimal places, 1.221, 1.221, you can see even the truncation error is at 3 equivalent. They are equivalent at 3 decimal places. So you can see how this continues. So let us take one more iteration when n is equal to 2. Permit me to clean this part. Let's take one more iteration. This is how we continue using the second order, second stage or two-stage Runge-Kutta formula for solving initial value problem in ordinary differential equation. So you can see how these initial conditions are given. Now we are looking at n is equal to 2. When n is equal to 2 plus 1 is 3. So you are going to have y3 will be equal to n is 2, y2 plus 1 all over 2 into k1 plus k2. So at this point, you extend the line a little, you have 3 here. So of course our k1 will be equal to our h is 0.1, then f into, of course, n is 2. So now at this third iteration, for us to get our x3 will be 0.3, because for you to get that value, you are going to have x3 is equal to x2 plus h, and that is equal to 0.2. Our x2 is 0.2 plus 0.1, h is 0.1, that is 0.3. So our x3 will be 0.3. So when you come here now, if you have this, so when you now talk about when n is equal to 2, our x2 here, this will be h is 0.1, f of course n is 2, that will be x2, which is 0.2. Our x2 is 0.2. Then we now come here, our x2 is 0.2. Then our y2, of course we are using the y2, is 0.2. Then our y2 will be, look at the y2, the theoretical, the numerical value for y2 is 1.221025. Then you close the bracket, we are talking about k1. Then of course you have 0.1 times, since our f of x, y is y as given by this problem, we take only the value of y. That will now be times 1.221025, and that will be equal to, so our k1 at this point, will be, when you multiply 0.1 by 1.221025, you have 0.1221025. That will be our k1, 0.1221025. Now let's go ahead to get our k2. Our k2, of course, h is here, h is 0.1. Then you put your f into xn. Since n is 2, it will be x2 will be 0.2 plus our h is 0.1. Then comma our y2 is 1.221025 plus, then of course our k1 is 0.1221025. Then you close the bracket. Then our k2 will simply be 0.1. Then when you add, you have your f, 0.2 plus 0.1 is 0.3. Then you put your comma. This will now be the value for x, and our x is not part of our y prime, it's only the y part we need. So 1.221025 plus 0.1221025 0.1221025. That will give us 1.343, 1.343, 1.343, 1275. You close the bracket. Then of course our K2 will be 0.1 times. Since we are needing only using our f of xn is y, we are using only the y part times 1.343, 1275. And when you carry out that multiplication, you are going to have our K2 to be 0. It will be equal to 0.1343, 0.1343, 1275, 1275. So that will be for our K2. This will be for our K1. So you can see how we are making progress. Now we can now come and put these values here to get our Y3. So our Y3 will now be equal to, just follow the trend. It's as simple as ABCD. It's very, very simple. Once again, please subscribe to my YouTube channel, Dr. Chris Isekaibe. Share my videos in your social media platform. Like the videos, make comments. If you want me to add anything that will make the channel to grow, please put it in the comment section. Your comments are welcome. Thank you for all the comments I've been receiving so far. If you have not yet subscribed, please do that subscribe and be part of those sharing knowledge across the globe. And as you do, God will bless you. Please wait patiently as we gradually come to the end of this particular topic. Now, we want to get the value for K3, for Y3, since we have value for K1 and K2. So Y3 will now be Y2. Look at the value for our Y2, 1.221025, which is our Y2, plus of course our 1/2. We normally put it in decimal 0. Then our K1 is 0.1221025 plus our K2 is 0.1343, 1275. Then when you carry out this arithmetic, when you carry it out, you come here, you now find out that your Y3, when you add these two multiplied by 0.5 and add it to this, our Y3 will now be 1.349, 233. That is what our Y3. So we are taking it up to 6 decimal places. You know, one beautiful thing about numerical analysis, don't cut off or round off so many numbers. If you round off so many digits, you are committing inherent errors. It will make the truncation error to be larger. So to reduce the truncation error in numerical analysis, what we do, we try as much as possible to take more decimal places. That's the only way we can reduce the inherent error. For instance, you can see me working with 6 decimal places. So if you have a very good calculating aid that can take up to double precision 20 decimal places, why not you use it, especially if you are using computer programming. If you are using Fortran programming language, for instance, I use Fortran a lot. I take 20 decimal places, we call it double precision. So you can take as many decimal places as possible so as to reduce the inherent error. By the time you are now adding inherent error at each stage of calculation, it will make the truncation error to be bigger. So you try as much as possible to reduce error. The essence of numerical analysis is to get alternative results using numerical methods that will not be different from the result gotten using the theoretical or the conventional method. So now we come here, our Y3 is 1.349233. You can see how that has been gotten. Now permit me to get our theoretical solution so that from there we can get our error. So if I want to get my y of x3, this will be equal to exponential x3, and that will be exponential 0.3. Our x3 is 0.3. All you just need to do is use your calculator to get exponential 0.3. So exponential 0.3 is 1.349 is 1.349859. 1.349859. You see that? 1.349859. So you can as well write it here, 1.349859. That is our exponential 0.3, and that is the value at the third iteration for the theoretical solution. Now, of course, the truncation error is the theoretical result minus the numerical result. So one, you can see at 3 decimal places they are equal. 1.349, 1.349. You can see it. So the difference will now be 0.000. That is, the error will be 0.00626. That is what you have. So you can see that is what we have as the truncation error. The truncation error. Well, the truncation error is the difference between the result from the theoretical solution and the result from the approximate or numerical solution. So, beloved, you can see how we have been able to use the second order two-stage, or you can say second order second stage explicit Runge-Kutta formula or method to solve this initial value problem. Y prime equals to y of 0 is equal to 1, and the interval, you can see the interval given is that we are starting at 0, but we are going to stop the value of x. You can see there are 7 more iterations to go. If we continue like this, that is where the computer software is necessary. If you get to be the computer software, you are using Fortran programming language, or even MATLAB, or even Maple. All you just need to do, just write the program, and the program will run the results for you. So we have been able to solve up to just 3 iterations. You can see we have spent quite some few minutes doing this. If it were to be a computer program, you just write the program and you can even get hundreds of iterations. And for this particular condition, this is the initial condition given for x. It's starting from 0 and it's ending at 1. That means we need to get from 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0. That is 10 iterations. And we have done just 3 iterations. Now look at the situation where h is equal to 0.01. How do you now know the number of iterations? It's simple. Just say this is our b, this is our a. The number of iterations is b minus a all over h. So if you say 1 minus 0 is 1 divided by 0.1, you have 10 iterations. If you have this to be 0.01, if h is 0.01, you divide 1 by 0.01, you have 100 iterations. Imagine you having 100 iterations. All the time we have been spending is only 3 iterations we have been able to solve. Or for instance, your h is 0.0001, 1000 iterations. 10,000 iterations. How do you solve that? That is where the computer comes in. The computer comes in, the programming language. That is where it comes in. So, I believe you have learned something very useful today about the Runge-Kutta method. We have the third order Runge-Kutta method, we have the fourth order Runge-Kutta method, we have the sixth order Runge-Kutta method. I am a specialist in Runge-Kutta method. I have series of explicit and implicit Runge-Kutta formula that I derived. And one beautiful thing is that these initial real life problems can be transformed into a first order initial value problem. Then you now use the Runge-Kutta method to solve the problem and get your results. God bless you for listening patiently, watching the video to the end. Please subscribe to the YouTube channel, Dr. Chris Esekagbe. Click on the notification button so that anytime I upload a video, you have a notification. Like my videos, share them in your social media platforms, and as you do, God bless you. God bless you. If you have anything you want me to do, for instance, you are a research student, you want my input in your research in numerical analysis, in statistical analysis, why not consult me? I will be part of your research work. I will be glad to hear from you. My contacts, you'll see them at the beginning of this video. God bless you. Have a great day. Bye.